All right, so this is something we covered last class, and I wanted to make because we are behind, we could not cover or we could not finish the question, so I'm just going over again. So air stripping, this is basically the principle is you add contaminated water on the top, you spray them, or you let it percolate on a on a solid surface so that it exposed to air, and as it moves through that surface, the volatile pollutants can permeate out of the liquids and get into the air. And if you are blowing air from bottom to top, those air will pick up all these pollutants and then you'll capture that contaminated air. In the process, the clean water is going to be collected at the bottom. So that depends on how fast the pollutants can migrate or transform from liquid to gas phase, or which is air here. And based on mass balance, this is written here. Some of the pollutants that remove in water has to be some of the total amount of the pollutants that get into the air. So when you equate that one, you come up with a term or dimensionless constant, which is here S. S is called stripping factor. So dimensionless constant means it doesn't have any unit, because Henry constant, the one is written here is unitless. Then it's the ratio of airflow divided by water flow. So this gives an indication of how efficient the system is. If higher the stripping factor, the more likely the pollutants can be stripped out of the system. Um, so typical range is 2 to 10. Um, S equal to 1 means at least there is a pollutant that removed from the water. But typically it's not efficient. Systems are not efficient, so that means you have to design it for higher S factor, which is a 2 to 10. Typically, you cannot make it higher than 10 because become very expensive. Because if you see what makes the S higher is not Henry constant, because Henry constant you cannot control. That's specific to the pollutants. The only way you can make it higher is if you lower the water flow and increase the airflow. And when you do that one, if your airflow is much higher than water, or it's disproportionately very high, you can blow out all the water. The water will not drop down. It will more likely it will stay ponded on the surface. So that's the basically the visualizing this treatment. So any kind of design, any kind of systems you can design based on this aspect. So these questions is given everything. Henry constant is given 128 atmosphere pressure, but then you have to change that to dimensional less constant. And so learn how to do that one from CEE163. Basically, you use a partial pressure or gas constant. Pressure times volume is equal to number of mole RT. So if you know the Henry constant in atmosphere, then you can convert to um, dimensional constant using these equations. So I think we learned that one in the C153, or just check online because we don't want to cover. But I know I have given the equations here. That equation you can substitute directly, and you should be able to get that number. So this Henry constant, dimensionless constant is a H star. So you're looking for H star. And so if you know the pressure and other things, you will be able to find. So for instance, here, this is an atmospheric pressure, the H. So if you just plug in these equations, you should be able to calculate that. T is temperatures of the water temperature. Is in this case is 15 degrees Celsius. So you have to change that to Kelvin, 273 plus 15. Then this is the specific gravity of water, which is 1000. And then 18 is the molecular weight of water, which is 18 gram. So if you put this equation, you convert that to H prime. So which is here 0 0.0, H star is 0.098. Then everything else you can solve. So we solve that one here. Um, you know the stripping factor, that means you know these equations. If you know the equation, you can solve for one of the unknown. So that's what we did here. We solved for the unknown. Now, question is, what's the design? What's the diameter it should be? As I said, you know the Q. If you know the flow rate, the the water that you are adding divided by loading rates, you should be get the area. The idea here is that you don't want to add lots of water on a airstripping tower, because if you add too much water, the transfer rate will not be efficient because it has to touch enough air. So that's why the loading rates are kind of defined. It says that you cannot add more than 20 gallons per minute per unit square feet of the area. So anytime you have to, when you have to think of the design, how wider it can be, if you know the flow rate, you should not make it so narrow that you are adding more than 20 gallons per minute per square feet of the area. So that's just written as a control so that you know how you can add that one. So again, this is assumption.
Wait, sorry, was the typical loading rate is that for how much air you're adding or how much water you're adding?
So typical loading rate is the amount of water you are adding, because
Okay,
what
thank
you
you.
are treating is water, not air. Because that's so loading rate is, imagine you are pumping groundwater, so it's all connected to groundwater. So how much groundwater you are adding to the system per square feet. So that's why the unit is gallon, because you don't really measure air in gallon. Most of the time you measure air by cubic meters, not gallon. So that's also another way to um, check that one. So this is groundwater. All right, so now you learn, if you know the stripping factor, if you know the loading rates, you'll be able to calculate the area and all that factors. But that doesn't really tell anything about how high, how tall the stripping tower would become. So that height is the equation is this. Okay, so I'm going to explain conceptually what does that mean. So height is basically, it says STU times NTU. STU is the height of transfer unit, means imagine you have a imaginary one unit, means think of one bubbles is one unit. Or if you pack, so in the entire the stripping tower, you are packing the small column, right? Small um, in the handouts, you can see that there are different shape of these beads that you pack. The idea of this bead is that higher the surface area, as the water flow across it, it exchanges more air, or it exchanges with in contact with more air. So each of that little beads is one unit. Give me a second. Okay, so transfer unit is basically that each bead. So this one is one transfer unit. So imagine that you have beads, that bead area is the area available for air exchange. So what it does, it you can calculate the transfer rate for that one bead, and then you multiply how many transfer unit you need. So you multiply that, so add of them together, it becomes the total height. And so that's the concept. Okay, so it's imaginary stuffs. So height of transfer unit, that based on this equation. So I'm just going to explain what that means. QL is the amount of water you are adding, okay, or hydraulic loading rate, or the whatever you that hydraulic loading rate means the water loading rates, and KL times A is the mass transfer rate of pollutants that going across the system. So basically, if you have this, let's say this is the transfer unit, and what does it? All the water will flow across it. So imagine this is water, okay, as it moves. So let's say water is being poured. So this is how water will move to one to another. So this is how the water is moving, okay. And so as it water moves, the air is going to transfer, the pollutants will transfer from air. So this is air, right? So the pollutants will move towards the air. So you are looking for that transfer rate at that unit. So KL is the transfer rate, liquid phase mass transfer coefficient, which is the number is given 0.01 to 0.05 1/second. So it's a first order reaction, the rate. So that means it's removing within that time frame. So that's 1 hour time. So what it means that these numbers are already given to you. The KLA is given. That means you can calculate HTU. Once you calculate HTU, you can multiply times the number of transfer unit, which is these equations. This equation again is a function of stripping factors, concentration in, this is amount, whatever the concentration coming in. Then you have this is gas concentration in, so this is the amount of contaminant in the gas or the air phase. Usually this is zero, so Gn, this is the concentration of pollutants in air going in. Usually this is zero because you are not putting a contaminated air, you are putting a clean air. So you can put all that and it becomes simplified versions. So if you do that one, this would be S by S minus 1 log C in by C out times S minus 1 by S plus 1 over S. All it means is the what it says, the number of transfer unit depends on the difference in concentration of pollutants in and out in water. So this ratio is what it depends on. Then you have also stripping factor is another constant here. So that means if you know what's the your desired output concentration, how much pollutant that you want to have in the effluents, you can predict that NTU, number of transfer unit is, and then you know the STU is the height of each transfer unit. That's based on the mass transfer rate, and then you multiply them, you get the total height. So let me see. There was a question on chat window. Now, S is the stripping factor. That's the one we learn here. This one. This is basically how efficient it is to remove pollutants if you know the flow rates. Okay. All right. So these two terms. So again, the questions are going to be asking for looking for this height. Just plug the value, you will get the answer. So we'll show one example. So I have Excel file that I'm going to share, not share in the sense that's what you are going to do in your homework. So these questions is related to exactly homework. So the answer in the homework is this. In the sense you'll make this graph using the Excel file. So I put all this value here. So this is the C in is the amount of pollutants coming in groundwater. C out is the treatment goal. That means this is what your effluent concentration should be, or this or lower. So that means the removal is basically C in minus C out by C in. How much percentage you remove by times 100. So in this case, it will be 1500 minus 30 divided by 1500. So that will be the amount removed. So that will be 15 minus 13. So that will be, let's see, 1470 divided by 1500. So that would be 98%. Okay, so that means you are removing 98% of the pollutants that coming in. Then G is the height given, because normally the air tower is already designed, right? So that's the height 10 is given. Then it says the D, what is the D here? 0.6 meters. That seems like the diameter. I have to check what exactly it is. KLA is the mass transfer rate. This is the water flow rate, water flow. This is the air flow, and this is temperatures. So these are all given, and then you have also given this different pollutants. And if you are given different pollutant, you also know the Henry constant, because this is something you can search online. There is a website also given in that links that I provided, either in the homework or somewhere, or you can search online. That's easy to find. And once you plug all these value, you will be able to vary airflow rate, and then you can plot G, because if you see the G equations, STU times NTU, this has everything. Okay, because airflow rate is a function of S. S has the S equal to H star Q air divided by QR. Okay, so that means all these variables are here. You just plug, keep everything constant. You can vary. You can then plot G versus Q air just by using that equations. And then you can plot this value based on different number of airflow rate. So what it means that if you see this graph, how to read this graph? If your height is 10 meter, that means you can, as you see, as you increase the airflow rate, your effluent your this data is the amount of height needed to remove that or meet that effluent concentration. So what it means that if you are increasing the airflow rate, you don't need a bigger or taller air stripping tower, because it is becoming more efficient. So as you see over here, if you have a 10 meter of height, you can remove most of these pollutants, as long as the airflow rate is below 95.88. As you increase the airflow rate, then the height needed to remove that pollutants will become smaller and smaller. So this is basically saying that if you have a 10 meter height, what you can remove, what you cannot remove, based on different airflow rate. Let's say your airflow rate is another way to read this graph is, let's say your airflow rate is 150 liter per second. So let's say 150 liter per second. So if you draw this line over here, that means if your airflow rate is 150 per second, that means only the pollutants that's removed is PCE, because at that rate, this is the only one that has a that doesn't require more than or less than 10 feet or 10 meters. This one, this pollutant, let's say this is TC, this requires almost like little more than 10 meters. That means it will not remove completely. The other one, next one is a ethyl benzene. It requires almost a height of near 11 meters. So that means if you have designed 10 meters, you are not removing most of them. So this is another way to read it. So again, this is the same graph I plot different way. This time I fix everything. The only thing I vary is C out. So what I'm saying is, if you have a different treatment goal, how the height requirement will change. So I put all these equations. Again, these are the equation you are going to, these are the graph you are going to draw using Excel file, or using your whatever the software you can use, MATLAB or any softwares that can plot graph. So this is homework number 3. All I'm asking is you plot this value, G value, varying multiple different variables. Either fix everything one constant, then vary something else. That way you can see how things are changing. Any question? Let me see. These are the value to remove 98%. Yes, the one I saw in the very first graph. These are the value to remove 98%. Okay, let's see another example questions that could be something like in midterms that you got in 2 years ago. So a pad column air stripper is designed to reduce chloroform concentration in the extracted groundwater. The concentration is to be reduced from 50 milligram per liters to 0.05 milligram per liters. So you know that that means you know the C0 is 50 milligram per liter. C or C in is this, C out is 0.05 milligram per liter. Okay. Size size the air stripper by determining the air flow rate, cross sectional surface area, and packing height. Use the following information. So most of things are given. Henry constant is given. That means you can calculate H star using the equation I provided. And the last time we calculate, if you remember, the value was 0.098. If you see 0.098. Um, so then, let me, sorry, I don't know why the phone is coming even though it's silent mode. Okay, so let's see. Stripping factor, that's given, which is S. Temperature of water is given. That means you have to convert that to Kelvin. So 298 Kelvin. Extracted groundwater flow, that's QW. KLA, that's mass transfer rate. Type of packing. So this is it says what kind of packing. So this one is basically from your handout. That will tell you any kind of configurations, but it's not needed anywhere. We don't need that one. It just says that what kind of beads you are packing. Unless there is a very specific type of constant that you need, then you need that one. Hydraulic loading rate, that's QW. So if you see where we need that one, this is QL, hydraulic loading rate. QL is um, so the difference between groundwater flow rate and hydraulic loading rate is that you are pumping this much water, but how you are adding per unit square feet is the hydraulic loading rate. So that's you are spraying across the stripping tower. Chloroform concentration in the influent air. So that means C in or the G in equal to 0. Okay. And so that means you have to calculate all these other values. So if you see over here, everything is else is given. QL is given, KLA is given, S is given, G in equal to 0. So that means you got every numbers. So all you have to do is put all these value and calculate G. So there is really not much to change here. That's how you can calculate G. NTU, number of transfer unit time, height STU. And then this is a function of S, C in, C out. What else? QL, KLA. So everything else is given. Then you should be able to solve it. By the way, the handouts that I provided, they have also examples. So you should look at those examples for us to learn. You're right. This is 288. I made a mistake here. 288 kelvins. There you go. So if you see what else is asked, that's the height. It says what's the cross-sectional packing height. Packing height is G. So that's one. Cross-sectional area. So that's basically area of the stripping tower is, as you know, Q divided by loading rate. So loading rate Q is given, which is 120 GPM. That's the amount of water you are, and then the hydraulic loading rate is 220 GPM feet square. So that means it will be 60 square feet. Okay. 60 or 6? This is 6. So all I'm saying is that the area should be maximum 6 square feet. And then if it asks um, how do you get the square feet, no, you can look for the diameter. If you look at the diameters, is the because it's circular usually, so pi d square by 4. Then you can solve for the diameter. So the what's the size would be. Any question? I don't know what else being asked, but it's seems like straightforward everything. I'm just going to write the answer here. The type of answer you're getting here, the final you should be able to get is 40 feet if you solve this one. If you plug all this value. So let's see now. So the questions are very much um, you will be given everything. The challenge or the only challenge here is to know what terms are what. It's really you are not doing anything else. But so these steps are written here, the solutions. I'm just not writing here. The things that you have to check is what kind of quiz questions that you may get. Um, so let's see, there are a couple of quiz questions you can get from here. How do you increase the removal of pollutant in a stripping tower? What kind of design factor? So think of this way. If you have a design, you can obviously make the stripping tower taller and taller, but most of the time that's designed, that's fixed. You can't really change it. So as an operational parameter, so design factor, you can obviously increase it. As you increase the G, you are adding more. You can increase the removal. Same thing as you increase the width, you are spraying water more efficiently, and so that means if the area is increases, that means you are also going to increase the removal rate. Another thing to think of is the design is how um, what's the size of the bead. So if your size of the bead, the surface area is very high, that means you have more area for the contaminants to increase. So that's KLA. So this is the transfer rate. This transfer rate will be much higher if the beads has higher surface area. So these are the few things you can design better way. But then what are the operational parameter? Means once this is fixed, you pack the same, you already fix, you would already design it. How you can operate it such a way that it has more removal. So think of water flow. So let's have a quiz question. Imagine this is a quiz question. So you guys tell me the answer. If I increase the water flow rate, what will happen? Is this going to improve the removal or it's going to not improve the removal? Yeah, I see some, it is not going to improve it because if you see if you're adding too much water, then it doesn't have enough time for the pollutants to diffuse out. So that means if you increase water flow rate, removal decreases. And if you see where it is coming from, look at the stripping factor. Stripping factor is Henry constant times Q air, Q world. So that means you're stripping more efficiently if your water flow rate is low. Okay. Same thing airflow. That's exactly opposite. So if you increase the airflow, removal increases because you are transferring more efficiently. So the third one, mass transfer rate. If you make the mass transfer more efficient, the removal will increase or decrease. Removal would increase because again your goal is to make the pollutant move faster from water to air. The last one, height. If you increase the height, The removal would increase or decrease. We just discussed it just now. All right, so that's going to increase because the water percolate. You have more chance for that pollutants to get out of the water because it's long time for that to be exposed to air. So these are the quiz questions. So whatever the quiz question you think in the tomorrow quiz, those will be almost like these questions. Now, what will happen if you increase this versus that? So I just want to show that this is the third homework questions. You should try to solve them by Tuesday or by Tuesday, yes. Next class, next Tuesday. And so these are all given. So it's related to things that you are going to already learn in the class or you are learning now. All right, so that's it in terms of um, the the class that the question that I wanted to solve yesterday, not yesterday, last class. So I'm going to now cover the what is this? Yeah, it's part of the questions. So it has all these different factor given. All right, so next class, which is today, is in situ treatment technology. Let me share a different slide. So lecture 7 in situ. So we are going. So what we learned so far is ex situ, where we are pumping all the contaminated water and treating it outside the aquifer. Now we are going to learn mostly how you treat inside the system, and this is mostly in situ treatment technology is more popular because it doesn't. It's less. It's not expensive because you're not pumping that long. But then it has also efficiency can decrease based on whether you can reach out, whether you can actually um, deliver the reactants or the stuff that you need at the polluted locations. So it's kind of a black box. So what you're going to learn, there are two specific technology you are going to learn. Advanced oxidations, another is principle, the bioremediations. Bioremediation, we are not going to learn today a lot. We are just going to go through overview of it. But next class, we are going to design bioremediations. So today, mostly you are going to design the advanced oxidations, which you already know in terms of how to solve the questions because the homework two question is advanced oxidation to some extent because it's basically you have equations, you know the moles of pollutants there, and it can be treated by moles of oxidants, which is permanganate. What you're going to learn in this class is the concept and how to decide which oxidant to use. A couple of things announcement about today's class is homework is due today, but you can submit tomorrow if you want. The submission window will close tomorrow midnight. So even you are one day late, I'm not going to take any. I typically don't take any points off if you are late unless you have to tell me that you need that extra time for a specific reason. Quiz 2 is next class. Again, that's not in the class. I'll release the quiz on the after the class, and that's on lecture 4, 5, 6, 7, including. So today's lecture is 7. So that's including everything that we covered today. But you can ask any of these questions related to these lectures on campusware, so that just in case you have any doubt. Again, this will be released after the class around 6 to 7 p.m. I usually send email when I release it. That way you know when to open it. You have 20 minutes window, 10 questions. This way you also get enough time to answers. It's very similar to homework, the quiz number 1. And I noticed that in quiz 1, at least one student had difficulty is because when I asked the question A, B, C, D are reshuffled by CCLE. So pay attention to what is written because a lot of times question A, I write A, answer A, capital A. And that A can be varied for B or C or D or all these, they reshuffle it. So a lot of times don't just write A equal to A. No, I don't know. I'm making it confusion. So let's say A, B, C, D. That's what in CCLE. If the answer is A, B, C, D, this this number can change. A, B, C, D can be reshuffled for different students because that's how the CCLE does. So pay attention to what the answer and just select that one, whether that's first or second or third choice or fourth choice. Those are reshuffled in the CCLE. I know one student suffered because of that last time. I try not to ask questions like that so that you don't have confusion. All right, so office hour is at 2 to 3 p.m. Every Monday. So I know last this week some of you join. You can attend office hour, ask any questions. A lot of times you can ask questions related to projects and anything else. And project outline, the which is due on February 4th. That's next Thursday. So you have 10 or 12 days to finish outline. And for outline, you need definitely my help as well as TA help. Because what it does, you set the tone for the project. Then after outline is done, you are just writing. You are not really changing much. So it's very important to make the outline very specific. That way you exactly know what to do. And so this is the way to go for outline. Decide overall narrative of the work, what to area to include, what not to. That's something I you can discuss with me, so that I can help you to know whether this is good enough or this information is available online for you to work on. Once we have outline, and during the outline stage, we assign different student different tasks. That means different section will be done by different students. That way, as a whole, you can finish the project much faster. And then once you assign each member a specific section of the outline, that member will independently search online or materials to collect all the information they need to write that sections. And that each members will write their topic sentence of their paragraphs and add some kind of links. So for instance, let's say you are searching for bioremediations and you find multiple reports. You can just paste those links. That way next time you know that these are the links you need to read to write those paragraphs. And you can also link to the journal articles that you are going to cite. So these are the things you can do. And you can also start adding questions and stuffs for your team members. This way, they can all also give feedbacks and work as in the Google Doc so that every students can see what other person did. That way, they can give feedback to each other. And set a Zoom link with your team members your own way, and then invite me or the TA when you are ready. That way, we can discuss for 15-20 minutes. I'll see the outlines and I'll give you some feedback, and that way you can continue to improve it. And I already am meeting with one group on Thursday um, to discuss about topic as well outline. This is a continuous process, so it's really not. You can set a time anytime. Any questions for the outline? Okay. All right. So let's get to the point what we are going to cover today. We are going to cover ex-situ treatment technology, which is the difference between in-situ and ex-situ. As I said, you are not pumping anymore. You are only injecting reactants at the pollutant location so that you can remove it. So you already know ex-situ remediations. We cover it. The in-situs are basically you are selecting the sites and doing it at the locations. For instance, if I put this graph here, if you have to choose which one, if you have to identify which one is the in-situ, which one is ex-situ, how do you know? So let's say I'll give you one example. Air stripping. Air stripping, you see all you are doing is you are pumping water and you are treating here. This is the where you are spraying water on the top and you are treated water coming out. So again, your treatment happened outside the groundwater aquifer. So that means this is ex situ. What about this one? Soil vapor extraction. Is this ex situ or in situ? If you see the way the picture is, it's really not. Um, or let's say Emma says ex situ. Yes, because all you are doing is pumping. Anytime you are pumping, that's the way to find out. If you are pumping water outside, it's already ex situ. Okay, um, but let's think this way. What exactly happening here? Are you pumping water or are you pumping something else? If you close, if you if you look closely, you are not pumping water. You are pumping water. You are pumping in the subsurface soil. The water you are not pumping. So this is basically you are just selectively removing the pollutant itself, nothing else. So that means this is also an in situ method because you are not really pumping water outside. It's just the picture is misleading because it's very easy to see that this is you are pumping water. Let's take this one. Gas purging. What you're doing here? Are you pumping water outside? Okay, so this is in situ. Brandon says in situ, and Adriana says, which is correct. If you see there, all you are doing here is you are basically um, injecting air into the contaminated water so that you can if there is a volatile pollutants, it can just permeate out of the soil. So basically, clean air is going to replace the contaminated air, and contaminated air is going to diffuse out of the ground. So so here you are not capturing the pollutant directly. You are just letting it get into atmosphere. Now let's look at this one. This phytoremediation is in situ or ex situ. Right. So many of you write in situ, which is true. So if you look at both phytoremediation and bioremediation, both are in situ because you are not really removing neither you are taking the soil out or neither you are taking contaminated groundwater outside the system. So many of your projects will use these two technology if you are looking at contaminated site because long-term decontaminations is mostly done by these two technology. If you are very highly polluted and plants cannot grow or bacteria cannot survive, then obviously you need something chemical other method. So so now you learn how to identify whether in situ or ex situ, and but based on this process, you will develop the understanding of what method to use. So again, the principle of in situ technology is you do not dig the soil or you are not pumping water. So those are the two most expensive method. So that means your energy cost is down. But in situ method means you are adding a reactants at the site to destroy that pollutant, and that reactant could be biological or that could be chemicals. In advanced oxidations, you are adding chemicals. In bioremediations, you are adding chemicals, but not in the sense you are adding nutrients and substrate for the nitty microorganism to grow faster. That way, they can degrade those pollutants biologically. A lot of times, it is also you are injecting particulars like nanoparticles. Small fine nanoparticles has very high reactivity surface. So, for instance, zero valent irons. When you inject those, if you can inject them, let's say, assume that you can inject them, then those particulates have so high surface area that it can bind a lot of pollutants. And not only that, it can also degrade a lot of pollutants. And zero valent iron is just one nanoparticles. The newer technology is people are adding activated carbon. So you're very fine, 100 nanometers or lower than that, and basically carbon particles, and you are pumping them at high pressure. So they will deposit on the fractures, and that's how they can capture a lot of pollutants. And a lot of times they also mix this activated carbon with a biological organism like bacteria. They inject them inside. So the idea here is that this activated carbon will capture a lot of nutrients, and this bacteria will eat them away because they are sitting there around, and that way this activated carbon become more or renewed to remove more pollutant. So these are different types of technology. So when I hear your outline or your side problems, then I'll suggest some of this for you. So that's why this meeting is essential to discuss about all possible treatment options for your sites or for your problems. So in situ chemical oxidation, let's cover this one quickly because we already know the concept theory. We are just going to learn about the practice. So in situ chemical oxidations, as you see over here, you are just adding oxidant. So you know already in the water treatments where you add permanganate or hydrogen peroxide or bleach in water and then you can clean them. In this case, you are injecting them into ground. So as you see over here, there are these wells. So these wells has this the opening over here. So you just pressurize them. And the idea first thing is to find out is where the pollutants are so that you can actually put the well at that location. So that's the design challenge to identify what the locations because you don't want to inject oxidants in a non-contaminated area. So once you know, you are just pumping it. So the what's the most difficult part of this treatment technology is identifying the hotspot. And second thing is to deliver the oxidant right at locations because as you know, oxidants are very reactive. So that means if you are injecting and in a soil, those soil also react with those oxidants. So if the oxidant is flowing with time, the 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 intensity or the reactivity of oxidants will decrease because of their reaction with the surrounding soil matrix. So that's why it's important to also know how we can make the oxidant last longer so that it can find that particular hotspot before it react with anything else. So those are the concept you will run in the next couple of slides. So again, in situ chemical oxidations is used for solvent like PCE, TCE, any kind of organic pollutants, petroleum hydrocarbons. It's not effective for PFAS. The reason is, PFAS is another pollutant which is very resistant to oxidations. Unless you use very high amount of this permanganate, other oxidants. So now one of the decision you have to make for your project is what type of oxidant to use. These are the things, different oxidants that's available on market. One is permanganate, hydrogen peroxide. Another is pentone reagent, which the difference is hydrogen peroxide mixed with dissolved iron 2. It creates a radicals, which is much more reactive than hydrogen peroxide. Then persulfate, and then the ozone. Ozone is a gas. So these are the 4 or 5 different things you can inject. There are advantages and there are disadvantages. So how do you design which one to use? The first one, if you want to think of what to use, you have to look for the most. If you use the most reactive one, it's more efficient. But the disadvantage of most reactive is you cannot inject further into ground because the moment you are injecting, the moment it exposed to the soil, it starts reacting. So that means you are very sure that this is the location you have to inject. So as long as you know that one, you should use the most reactive one. And what is the concentration of contaminants? Because if you have very highly polluted locations, you want to also use different types of oxidant, which one works more efficiently. Couple of things to look for is what's the byproduct, because oxidation, as you see, it destroy that pollutant to something else. And you have to also look for the byproducts is not more harmful than the original pollutants. The operational issues here is the delivery or efficiency. As I said, delivery means you have to look for the right location, and also it has to flow well because you are injecting with water. If it react with water, obviously you don't want to put it there. So delivery efficiency depends on also the whether it's a gas or liquid. So this is a gas. That means it's extremely difficult to deliver deeper into ground. So if your subsurface contaminants, it's really shallow, then you can use ozone. If it's well too deeper, then you can't use ozone. It's very easy to um, inject ozone, but it's very difficult for the gas to actually goes past that well, near the well, because of all the other aspect. All right, so now let's think of how to decide how much permanganate, hydrogen peroxide, what else to use. So these are the equations, the different way that the reaction happens. As I said, this is oxidant, means it oxidize pollutants. So let's think of this one, manganate. How many electrons it can accept? 3 electrons. Hydrogen peroxide, 2 electrons. So as I said, which one is more reactive? How do you know which one is more reactive? Based on these two. Any guess between manganate and hydrogen peroxide? Just by looking at these equations. You have to guess one. Permanganate, yes. The reason is, if you think of what is oxidant means, it remove oxidation means it permanganate. So this is for manganese, right? So that's manganate. Okay. Yes, you are looking for redox potential, but think of 1 moles of manganate will take 3 electrons. That means it can, it's basically how many electrons it can receive. That's the, assuming the thermodynamically is possible, it can destroy or it can oxidize three. Let's say there is a contaminant. So this is a contaminant. Oxidation means loss of electron, right? So how many electrons you can pull out of a so let's say it gives um, it minus electrons. That's the oxidations, right? So these electrons that something can pull up is based on how many electrons that oxidant can receive. So here manganate can receive 3 electrons. So that means if you have 1 molecule of manganate, it can receive 3 electrons for the contaminant. So that means it's more efficient. I'm not talking about the thermodynamically whether it's favorable or not. That's related to the redox potential. Just by looking at here, this is the most powerful is in this case permanganate, then hydrogen peroxide, and then but it doesn't talk about anything about kinetics, how fast they can react, but it's just it can receive 3 electrons. So that means if you are comparing, let's say, per sulfate, this is per sulfate. If you have a choice between permanganate and persulfate, you always going to use permanganate, because it is more reactive, because it can receive 3 electrons. So that's why you can compare. But again, efficiency is not about how many electrons; it's also how quickly it can react, how efficient it is. Hydroxyl radicals are more reactive, even though it takes 1 electrons. So this is just one way to look for it. But now let's say operational definition.
Sorry, Professor.
Yes.
Sorry to interrupt. How do we know, like, among those that yields 2 electrons, like which one is the most reactive?
You cannot know from this one.
Oh, okay.
You can only know how many electrons it can accept. That way you know how much more amount of permanganate you can add if you know the amount of pollutants.
Okay, got it.
So
Thank you.
another way to say is this is basically mass, how much mass of oxidant you need, or moles of oxidant you need.
Okay. So it's basically like a two-side question. Like
Yeah.
this is like the reaction side, but we also have to consider the receiving side to determine.
Not just receiving side, you have to also look for which one is more reactive. This doesn't say anything about reactive. This is more about, it says about how much of the oxidant is needed. So if you have the complete redox equation, we'll have examples, so you'll see that one.
Okay, thank you.
All right, so let's see. The next question is you got to use permanganate, right? So as you see, you are not using ions. You are always buying a salt. So this is you are buying either potassium salt or sodium salt. You can buy any of them. Okay. But what salt? Because what is essentially you do is you take this salt, mix with water, and inject it, right? And when you mix with water, they produce these ions. So what kind of salt to use? That depends on which salt is more soluble. For instance, sodium is more soluble than potassium salt. So that means, if it is more soluble, it's more likely to use it. So you'll always buy sodium salt. But if you buy potassium, it's not going to easily dissolve. So some of them will stay precipitated. So that's another one thing to think about. And second thing, manganate is used um, because it's denser than water. The reason why it is efficient, because groundwater is always at the bottom. So if you are injecting, it's very easy to pass through the subsurface and go down deeper and deeper. So if you have groundwater, naturally it will percolate downward, and so that means you don't have to worry about dispersing and spreading across the soil. One advantage, which can be disadvantage, is slow to react. That means it can retain its reactivity during injections, because slow to react, that means it doesn't going to destroy by soil. So that means when you are pumping, it will stay persistent for longer time. But as you see over here, these are the different equation that's possible at different pH. So when the pH is low, groundwater pH can vary between something around 3 to all the way to 10. So if your pH up, which is very acidic, it's very unusual. If your soil is around pH less than 3.5, this is the reaction. Manganese will produce um, manganese 2, Mn2 plus. The advantage is that it has 5 electrons, so that means it's very reactive at low pH, or it is more efficient at low pH. And also the end product is manganese Mn2, which is not toxic, so that's a good thing. But if your pH is between 3.5 to 12, look what happens. First, number of electron goes down, so it's not that efficient. But the other thing is manganese oxide form, which is a solid. So that means after reaction, you are forming these small particles, MnO2 solid. And because of that, in groundwater, this solid can start plugging or clogging the system. So if you are adding too much manganate, your end product is a very small solid precipitate that could also start blocking the pore. That means now you are blocking the wall, some area that will not be able to inject any more manganate. So these are the things you have to think of. So that means when you are injecting manganate, you have to also lower the pH. You have to add something else so that this precipitate doesn't form. So that's just the one little thing to think about. Another thing to think is in the very uh, in the in the very first reaction, you have H plus. That means it depends on pH. If you increase the pH, your H plus decreases. That means it become less efficient. This is also pH dependent. As you see, this is OH, so this is also pH dependent. The forward reaction depends on pH, but the last one, which is above pH 12, you are forming these reactions. This is very unnatural because no groundwater has pH more than 12. This is more about ex-situ treatment. The point here is you should know this equation, at least in the slide. When you see this slide, you should be able to say when it is dependent on pH and when the byproducts form that can have adverse negative impact. In this case, manganese dioxide can clog the system. All right, so let's see the what you learn from here, and we can say poll. Aquifer with a deeper subsurface zone is polluted with very high concentration of TC. Which salt or permanganate should be used? So you have two choices, sodium versus potassium. The difference is one is more soluble. If it is soluble, that means it can go deeper into groundwater. If it is insoluble, obviously you cannot inject because it will precipitate. So solubility is the advantage because that means you can inject with water. So as I said in the previous slides, I say one of them is soluble. That means that can go deeper. So that's the way to interpret this question. So we have 10 more seconds to answer this. All right, so I'm going to end the poll. As you see over here, sodium is more soluble. If it's more soluble, that means you can mix them in water easily and then can inject it to much deeper into ground before it precipitates. So that's why sodium is the right answer. So now what I'm going to do is I'm going to give the very similar example now. Then we can take a break for 10 minutes. So another type of reactant is Fenton reagent. Fenton reagent means hydrogen peroxide. When react with iron 2, it produces a radical, which is OH. The difference between this and OH minus is that that negative ion is not there. That means it has a radicals that takes, it's almost like electrons that you remove out of OH without having that pair, So it's like that's the difference. So this radical is very, very, very reactive, much more reactive than anything else. So that the advantage of this process is this iron is naturally present in any soil, many soil. So that means all you have to do is activate that iron by adding some hydrogen peroxide. So all you are doing is injecting hydrogen peroxide and the iron 2, which is already present in the ground, that can make it reactive. This is one way. Another thing is you can inject hydrogen peroxide and iron at different time. That way they are not, so basically you are injecting iron solution, that doesn't change anything. Or you inject the hydrogen peroxide first and then inject iron. That way you, whenever the iron meet the hydrogen peroxide, the reaction start to occur. So this is another advantage of injecting at a different time. So here iron acts as a catalyst to activate hydrogen peroxide to produce OH radicals. Again, this is effective below pH 3.5. So that means for this reaction to take place, you have to add something else to lower the pH. Okay. If you the reason why it is effective below 3.5 is above pH 3.5, iron 2 will precipitate out because iron 2 can react with OH, iron hydroxide. So if you increase the pH, that means OH ion is increasing, that you are precipitating this. So that means this iron is not available for the hydrogen peroxide reactions. So again, the advantage is stronger reactant than permanganate, but it's produce heat. So that means if heat is not desired, that means you may not need it. Another oxidant is persulfate. Persulfate is not very reactive. Oh no, it's actually the strongest reactive you see over written here. That means it's easy to inject because soluble, but come on, what is it? I'm saying all the different things now. It says easy to inject because it's a resolve. Phosphorus is slow to react. So why it is written strongest reactant? Strongest reactant. This is kinetics. This is about how effective it is. Okay. Like OH, the kinetic is less than seconds. In fraction of second it can react. So this one will react within like a few seconds, not few seconds, in less than a second, millisecond. This one takes longer. All right, so if I'm going to have this quiz just to, what we can do is we can arrange them in terms of reactivity. So I'm not going to ask this quiz, but let's see if if I'm going to say what is the weakest. This is weakest. This is mid-range. So let's not put the quiz as just know that this is the range based on how reactivity they are. That's why a lot of times if you have to inject for a deeper soil, you use permanganate. If you are using subsurface, let's say your street, if you are treating in the subsurface, use persulfate. This 208 2 minus. This is groundwater. If you are injecting much deeper into groundwater, use KMnO4. And within this range, you can use phantom. Okay, that's just for delivery system. But again, um, the reason is if you are using very strongest reactive substance, this will not go travel further than um, uh, few millimeter or few centimeter from the injection well. So it's not going to be efficient. In groundwater, you want the groundwater to flow to a distance and then to treat it. So this is one example. We already solved this one in homework 1 question. So I'm going to solve in very few, just going to explain what it is. The soil at a site is impacted by perchloroethylene, PCE. And the soil on the top of the capillary fringe contains 5,000 milligram per kilograms of PCE. This is the amount of contaminants in the, so you have 5 gram of PCE in 1 kg of soil. Okay. In-situ chemical oxidation is considered as one of the remediation alternative. Determine the stoichiometric amount of potassium permanganate that needs to be delivered to the impacted zone. What would be the amount if sodium persulfate is used? Okay, so I asked what is the amount of is needed to treat 1 kilogram. Let's say another way to think of this. So this is basically from here, 3 moles of PCE need 4 moles of permanganate. Okay, so KMnO4 is same as potassium. So that means if you have 4 moles of this, you need 4 moles of potassium permanganate. So I ask what is the amount of potassium permanganate is needed. So KMnO4 amount is for let's say 1 moles of KMnO4 is same as 1 mole of MnO4, and then you know that 4 moles of MnO4 is same as 3 moles of PCE, and then 1 moles of PCE is what's the amount, what's the molecular weight? So this is carbon is C2Cl4, carbon is 12 times 2 plus 35.5 is 1 chlorine times 4, whatever that number is. Let's say I'm just going to write Y, gram per mole. That means Y gram of PCE. Okay. And you are asked how much PCE you have in the 1 kilogram of soil. So that means you know that 5 gram of PCE, 1 kg of soil. Then you'll be able to calculate all of them. Okay. So the answer will be in moles per permanganate. So this is the same thing that you are given in the homework question. So you should be able to solve it. So I solve it. I don't really need to write it here. So let's take a 10-minute break at 15:25. Then we'll be back and we'll discuss about the principle of um, uh, so, okay, then we can discuss about bioremediations. There are some questions. I will cover that in the break. Let's see, do you need to, sorry, I think you went over this in a previous lecture, but why is sodium more soluble than potassium? Um, there is no, the why one thing is more soluble than another is related to is thermodynamic constant. If not like um, you cannot predict, but let's think of now why sodium is more soluble. So it's basically whether it's the affinity of KMnO for with sodium versus potassium. Um, that's again, it's a thermodynamic constant. We can a lot of things you can predict based on the electronic structure, but I would not go there. You just look for solubility. But here, if you let's say if you have to imagine why sodium could be more soluble, yeah, it could be because let's see. Usually the bigger the atoms, it's become less and less soluble. Okay, so for instance, sodium is always more soluble than potassium, and potassium is more soluble than cesium. As you go down in the periodic table, the atomic size become bigger and bigger. So somehow it strongly bind because the whatever the electronic configuration it has. But I don't think you should use that logic for everything. Just look for solubility constant.
Okay, thank you.
Okay. All right. I'm going to pause for. All right. So we learned about in-situ oxidations where you inject a reactive substance that will destroy the pollutants. The disadvantage of that particular system is although it can react with many pollutants very quickly, it can have unwanted consequence like it in soil you have many other things which are harmless, but then when they react with these reactive agents, they produce some kind of a precursor which can be also more toxic. And also it is very expensive, when you're adding injecting this pollutant, this reactive substance, you are adding a lot of materials to it. So that means it could also have unintended consequence. Other consequence would be it will destroy also bacteria or the native microorganism which are part of the ecosystem. So that's why if you like think of if you're drinking bleach, one of the one nobody should drink bleach. The something the reason I said it, we know last time we got a lot of criticism. Not we got criticism. There's um, because of corona there are some they thought if bleach can kill then why not we inject, which is obviously it's the wrong thing to do. We'll all die if we do that one. The same way if we inject all these oxidant into ground, you are killing lots of microorganisms which are helpful for other functions. So that's why in situ oxidation is the last um, method where you're there are just so much pollutants that you really don't care. You just want to remove them as quickly as possible so that once the pollutants are gone, the native microorganism will grow back. On the other hand, bioremediation is more efficient in that context. You're not adding any chemicals which are very toxic or in any way to native community. All you are doing here is you are injecting nutrients and substrate so that any microorganism naturally present there, you are just giving them a little bit of boost so that they can start eating those pollutants. A lot of the pollutants can be biodegraded. Very few contaminants like PFAS are not easy to biodegrade. So in fact, all these chlorinated solvent can be biodegraded. So that's why bioremediation by far is the most used techniques in last 10 years. So any system you are looking for, they always consider bioremediations. So we are going to discuss a little bit the principle behind it. Next class, we are going to actually solve problem. So I'll go through this quickly because this is something more concept or something more like understanding that you can relate to. So the design consideration for bioremediation is you have to think of what kind of microorganism present there, what kind of food they need, how much moisture they need, do they need oxygen or do they don't need oxygen? Because these are going to change the way you can design the system. For instance, some contaminants like chlorinated solvent, they are not easy to oxidize, they are easy to reduce. So in that context, you can, because chlorine can be reduced to chlorine gas. So in that context, you cannot inject oxygen. You have to inject something else that can help remove oxygen so that that reduction reaction is more efficient. So that means your reagent should be a reductant or something that remove oxygen from the water. Then also have to think of moisture, soil chemistry, whether the pH is optimum or not, because these microorganism will grow at certain conditions. So there is another treatment goals is you can also add this permeable reactive barrier where you can add zero valent iron or microorganism into that wall like you see over here. That's another ex-situ treatment method. So this could be so permeable reactive barrier. This reactive could be biological or chemicals. That means you can actually um, grow fungi or bacteria in that within that zone. So that could be biological reactor, or it could be also adding the specific zero valent iron or oxidant in that wall, so that it as it passes through, it will react in the system. One other treatment method, which is we are not going to discuss unless this is something part of your project. This is basically applied for subsurface soil. This is not applied um, for groundwater. This is mostly applied for source zone removal. For instance, if you have a polluted site on the surface, you apply this to quickly remove pollutants. And this is again electrochemical method where you are changing the pH or changing the redox state by supplying electron directly. So this system works mostly if you can oxidize or reduce at the electrode surface. An electrokinetics method is different from this in the sense that electrokinetic, you apply positive negative charge so that the ions can move from one to another. So electrochemical, the pollutant has to be oxidized or reducible. You cannot use this method if that cannot happen. For instance, let's think of this way. If you have arsenic, you have arsenic 3, arsenic 5, okay? And these are two different state, oxidation state. And one state is more soluble than other. So one of the way to quickly treat arsenic is by making them insoluble, by oxidizing or reducing this system. Same thing for chromium. Chromium can also, one of the chromium is more soluble than other. So that means you just have to convert that chromium into a state that is less soluble. That way they can precipitate out so that it doesn't stay in groundwater. For instance, let's say I'm saying that you have zinc. Can you use this method? Oxidation electrochemical method. Then you have to think of what zinc is going to turn into. Zinc doesn't have a soluble or insoluble oxidation state. That means this method is not efficient for zinc because it just doesn't have a soluble or insoluble ions. Okay, so let's see if we learn the concept now. So I'm going to ask this question again. Lunch. So the question is a groundwater aquifer is heavily polluted with heavy chromium or just chromium, doesn't matter. Which of the following treatment technology is efficient if the permeability of the groundwater is high? One of the things that, okay, you finish that, I'll discuss. So heavy chromium means, again, Cr6 plus. All right, so I'm going to end the poll here. This is a tricky question, tricky in the sense I didn't give you enough information. So any answer would be, logical in the sense permeable reactive barrier. Again, it works if the groundwater can flow through the system. If it cannot, obviously it can. So permeability, high permeability is important for this kind of treatments. Um, Electrokinetic, on the other hand, is actually more efficient if you have low permeable soil. Okay, I think we discussed that a long time ago. The reason is you don't want short circuit because the iron has to flow. If you have, let's say, very permeable site, the water will bypass it. So that's why electrokinetic is more efficient in the clay soil, which is a low permeable soil. And high permeability, as you see, permeable reactive barrier is more important. And in situ oxidations, the question here is, this require high permeability. As you see, this is permeable reactive barrier. So if the permeability is very low, it has to pass through that system. Electrokinetics, on the other hand, is more efficient, in fact, when it's not permeable. The reason is, as I said, the water will, um, the the iron has to move. Water doesn't have to move that fast. Okay, so that way you have enough time to work on it. In-situ oxidation is also efficient if the higher permeability is higher. But the reason why in-situ oxidation you cannot use here is chromium 6 is already highly oxidized. There is no way you can move to another oxidation. So you cannot oxidize chromium 6. It's the highest oxidation state. 6 plus is already very high. Even you add, you cannot remove electrons from it. So in simply, oxidation is not a solution here because you can't oxidize chromium 6. Okay. So in that context, you could choose any of them. But as I said, electrokinetic is more efficient when the permeability is low. So the answer usually is this, but again, as I said, I didn't give you the context, so it's very easy to get confused here. Phytoremediation will cover next class, other class, but just to show you, there are different techniques that you will learn in the phytoremediation. What makes the plants uptake pollutants, how they change the root structure in a way that they can remove pollutants, and some of the pollutants can actually migrate in through the plants and diffuse out of the system. So these are the techniques you will at least learn them in terms of the principle. One of the, I just put the quiz question just to explain here. Which part of the plant is more active area for phytoremediation of soil? As you see over here, most of the things happens in the root zone because that's where the first step to go through. So that's why the root zone has to be the most efficient method or the most effective or most active area. So that means anytime you are looking for what phytoremediation to use, always look for how deep the root can migrate. So any of your site, if your pollutant is way deeper in the soil, phytoremediation is not effective because root, the best grass we know can migrate maximum 6 feet. Some could be to like a 12 feet, but that's very rare. So 6 feet or 1 meter is the mostly the root zone. So anytime your pollutant is below that one, you can't use phytoremediation because they can't reach there. So that's one thing to think of. That's the whole reason I put it there. What we are going to cover in next class is a lot about biological process or the bioremediations. So I'm just going to give you some perspective behind it so that you can think of all this. So as you see over here, this is the a live bioremediation process in Gulf of Mexico where there was a oil spill. So as you see over here, these are the oils, And so one of the reason why bioremediation is not efficient in big scale is because you have to add all the nutrients in the larger scale. That's number one. Number two, not all contaminants can be degraded very efficiently in a system like this. For instance, here in the BP oil spill, you have so much oil that any microorganism present in ocean water will die because they can't survive in the. It's anything at very high concentration is very toxic. So the part of this picture why I really like this picture is you see this aeroplane, the what they're these are they're spraying something. Can you guess what they're spraying? They're not nutrients. They are not any kind of substrate, but they are something that will make the contaminant more diluted. That way, microorganism can be more efficient. So, any guess what they're spraying? All right, so I'm just going to write it here. They are they are spraying surfactant. Surfactant is basically, it makes the it will decouple the oil, so the oil will spread across very easily. So as you see over here, these are very highly concentrated oil, right? So you want to surfactant, or another way to say is dispersant. Dispersant. So that means if you have a oil, if they spread out across, that means the concentration will decrease. If the concentration decrease, the biology or microorganism, let's say this is bacteria, will be more efficient at being active and treating them. So that's what the bioremediation is now. So in next 2 or 3 minutes, I'll just give you some brief idea about what's the things to think about, and then in next class we are going to design it. So first thing to think of is the microorganism. And first you have to understand, this is not a biology class, so that means I'll just give you some ideas because there is undergrad class just on bioremediations. The first thing to think of is what these microorganisms do with these pollutants. They can actually use as a food and grow. If that's the case, you are in a good state. That means use that microorganism because that's what we call catabolism. Means they eat those contaminants and they will grow. And but on the other hand, sometimes we call anabolism when they don't really grow. They're using that pollutants to make some polymers or some kind of macromolecules, which is not really supporting their growth. So that means these are very expensive method for microorganism. So they are less efficient when you are using those kind of microorganism. So you have to distinguish what the microorganism does when you have a pollutant. And the second thing to think about is what's the electron source, or what's the food. So that's why you have to think of electron acceptor or source of electrons. Source of electron usually is organic carbon or contaminants. So organic carbon could be sugar. A lot of times they add sugar or any other kind of easily digestible, simple organic. So sugar, starch, and many other things they inject. So these are basically source of electrons. If it is aerobic, they inject oxygen. If it is anaerobic, they don't inject oxygen. They make sure that oxygen is consumed by some other way. So that means you have to think of what's the electron acceptor. So oxygen, nitrates, iron, these are electron acceptor. Then you have to think of the enzyme. What kind of enzyme is used for this particular reactions? So that means you can look for those enzyme activities. And so all the enzyme does is lower the activation energy for any reaction to occur. As you see in the oxidant, there is a activation energy is required. But if you have bioremediations, all these microorganisms, they makes it easier for to degrade some pollutants. So basically, they lower the thermodynamic barrier. And again, these are the different definitions. When you think of bioremediation, sometimes you hear biotransformations, biodegradation, biomineralization, all these other things are there now. So these basically based on to what extent reaction occur. For instance, Mineralization, right? Mineralization means you start with the chemical and product is carbon dioxide. So that's the inorganic constituent. If you start with organic and become, let's say, nitrate, nitrogen gas, carbon dioxide gas, that's become mineralizations. Transformation means it doesn't have to degrade completely. It's just transferred to some other different chemicals. So just like a removal of some functional group or that. So again, we clump together and say bioremediation if any of these things happen. Okay, so just to be aware of that. And one last thing you have to remember before last class is there are different types of pollutants. And some pollutant can be oxidized, some pollutant can be reduced. The chlorinated, which is here, chlorine, fluorine, all these bromine, these are the pollutant that can be reduced. They receive electrons and become chlorine gas or fluorine gas. So reduction can occur if you have fluorinated or halogenated organic pollutants. If you have anything else like BTEX or oil, they are oxidations. So that means you can add oxygen or electron donor. But if you are looking for halogenated compound, you receive electron acceptor. If it is metal, metal cannot be degraded. That means you can just lower the solubility or precipitate them out. So, or you can adsorb them to the organic, the cell wall. So these are the couple of different ways we'll discuss next class. So the last thing we want to do is this quiz just to see so that, so I'll not test you for bioremediations for the quiz, which is on Thursday. Everything before bioremediations, just to give you a context. All right, so the last quiz of this class before we stop sharing, relaunch quiz. Groundwater is contaminated with chlorinated solvent. You are asked to inject reagent to degrade or transform the contaminants. Which type of reagent you will use? Oxidant or reductant? So think of chlorine. Chlorine cannot be oxidized or reduced. That's something I just mentioned a few minutes ago. So it's based on that. So if you see over here, it says if you have halogenated compound, you need electron acceptor under anaerobic conditions. So that means you cannot oxidize. You need a reductant for that reasons. Okay. So these two are oxidant. This doesn't mean that they cannot. So the idea here is if your carbon chlorine bond, oxidant will attack this one, this bond. This bond, if you just want to remove chlorine, this is be reductant. Will attack this bond. Okay, so that's all in terms of the basic idea of bioremediations. Next class, we are going to design in the real world to see how you can optimize the degradations. For now, I think this is just the background. All right, so I'm going to stop share. Any questions? Okay, it's already 5:50. So I'm going to stop recording, but I'll stay here for next 5 minutes if you have to ask any questions related to projects or anything else.